Why would the US Air Force load a nuclear reactor onto 3 C-17 transport aircraft and fly it across state lines? The Ward 250 microreactor, divided into 8 modules and airlifted from March Air Reserve Base in California to Hill Air Force Base in Utah, marks the first time the United States has redeployed a reactor by strategic airlift. This video examines what that operation signals about military energy strategy, global force posture, and the future of nuclear power on the battlefield. If microreactors become standard equipment at major installations, the US military could insulate critical bases from grid failure, cyber attack, or missile strikes. If the concept falters due to cost, safety concerns, or political opposition, Washington may remain dependent on vulnerable fuel supply chains. Energy resilience is no longer a technical detail, it is a strategic variable in potential conflicts stretching from the Pacific to Eastern Europe. The Ward 250 was developed by Valar Atomics as a compact reactor optimized for modular transport. Its architecture relies on helium coolant and graphite moderation, with a core composed of tri-structural isotropic fuel. TRISO fuel contains uranium kernels encapsulated in multiple ceramic layers designed to retain fission products even under extreme temperatures. This configuration reduces meltdown risk and allows higher operational temperatures than conventional light water reactors. The design generates approximately 100 kilowatts of thermal output, modest compared to gigawatt-scale commercial plants, but sufficient for targeted military applications. Transporting the reactor in 8 separate modules reflects a deliberate logistical strategy. The C-17 Globemaster III fleet, capable of carrying roughly 77 tons of cargo per sortie, enables rapid deployment across continents. By demonstrating that microreactors can be airlifted, the Air Force signals that energy infrastructure may become mobile, not fixed. That mobility matters if forward bases face disruption from missile barrages, sabotage, or cyber intrusions targeting civilian grids. Historically, the US military has experimented with portable nuclear power. In the 1960s, the Army nuclear power program deployed small reactors to remote Arctic and Antarctic sites. Many were eventually decommissioned due to cost and logistical complexity. Advances in materials science and fuel encapsulation have revived interest. Modern TRISO fuel was tested extensively in high-temperature gas-cooled reactor research, with experiments demonstrating that coated particles retain structural integrity under stress conditions exceeding those tolerated by earlier designs. The geopolitical dimension becomes clearer when examining base vulnerability. Installations such as Kadena Air Force Base in Okinawa sit within range of Chinese ballistic and cruise missiles. In a high-intensity conflict near the Taiwan Strait, fixed power grids could be disrupted within hours. Diesel generators provide backup, but they require continuous fuel resupply, exposing convoys and maritime routes to interdiction. A self-contained microreactor reduces reliance on external fuel shipments, potentially sustaining command and control systems, radar arrays, and hardened shelters. Cost remains a central uncertainty. While exact program budgets are not publicly detailed, microreactor development requires specialized fuel fabrication, regulatory oversight, and security infrastructure. Producing TRISO fuel involves multiple coating processes and quality assurance layers that elevate per-unit expense. Critics question whether 100 kilowatts of thermal output justifies the capital outlay compared to renewable microgrids combined with battery storage. Proponents argue that the value lies in survivability and independence from volatile fuel logistics. 2 what-if scenarios illuminate the strategic stakes. First, imagine widespread deployment across Pacific bases. If microreactors are pre-positioned at hubs like Guam, Okinawa, and potentially rotational facilities in Southeast Asia, the United States could maintain operational continuity during prolonged disruptions. Energy autonomy would complicate adversary targeting calculus, as disabling grid connections would no longer guarantee blackout conditions. In that scenario, microreactors become force multipliers embedded within deterrence architecture. Second, consider a scenario in which costs escalate and public opposition intensifies. Transporting nuclear components by air raises security questions. Although TRISO fuel is engineered for containment, any incident involving a crash could trigger political backlash. If deployment slows or regulatory barriers mount, the Pentagon may revert to conventional fuel strategies while competitors invest in alternative resilience technologies. That outcome would narrow the innovation gap Washington seeks to widen. The redeployment to Hill Air Force Base also carries symbolic weight. Utah hosts advanced aerospace and logistics operations, making it a controlled environment for integration testing. By moving the reactor domestically before any overseas positioning, the Air Force can evaluate assembly timelines, grid interfacing procedures, and safety protocols. Demonstrating transportability under routine conditions is a precursor to potential rapid deployment in crisis scenarios. Globally, energy security intersects with military competition. China has pursued high-temperature gas-cooled reactor technology for civilian use, commissioning demonstration projects that also employ TRISO-based fuel. Russia continues to operate small modular reactors for remote regions and naval propulsion. The United States microreactor initiative thus sits within a broader contest over advanced nuclear engineering leadership. Control over compact, high-reliability reactors may influence both military basing and civilian export markets. Critically, the Ward 250's limited output underscores its niche purpose. At 100 kilowatts thermal, conversion efficiency determines usable electrical output, which will be lower. That scale suits discrete loads rather than entire metropolitan grids. The objective is continuity of essential systems rather than comprehensive electrification. In conflict modeling, sustaining communications, sensors, and hardened facilities for days or weeks can determine operational tempo. As the Department of Defense evaluates integration into base grids, the C-17 fleet's role becomes integral. Strategic airlift already supports humanitarian relief and rapid troop movement. Adding nuclear modules to its mission profile expands logistical doctrine. It suggests a future where energy assets move alongside aircraft and personnel, reinforcing contested nodes. Watch how regulators address certification, how costs compare to alternative resilience measures, and whether overseas deployment follows domestic trials. The first airlift of a modular reactor signals intent, not conclusion. In an era where infrastructure can be targeted as readily as forces, portable nuclear power represents an attempt to insulate military capability from disruption. Whether that insulation proves durable will shape how energy and security intersect in the next phase of strategic competition.